Hello and welcome to week 2 session of HSCI 6263. We have a lot to cover this week, so I'll keep this overview very short. This week would be focusing about events and probabilities, probability distributions, power and sample size considerations, and also type 1 and type 2 errors. You are expected to read chapter 4 of your textbook and the other two references that are indicated in the weekly session. Your assignment, which is the power analysis project, is due Sunday night. Please submit your project through the link provided on the assignments tab. And I just want to remind everyone that the power analysis project should be not more than 2 pages memo. And I really recommend you guys to watch the archived video on power analysis prior to working on your assignments. Before getting into the discussion of probability and distributions, here are some commonly used terminologies that I like to define. Population. It's a set of generally large collection of data points, characteristics, demographics, or items. Sample is a subset of the population. Random sample is a randomly selected subset of the population, and it's a representative of the population. Variable is a measurable, identifiable, defined characteristic of interest from the population or sample. Random variable is a randomly obtained variable from a sample or population. Statistics are summarized, calculated measure of a random variable such as mean, standard deviation, or variance, or etc. Parameters are counterpart of summarized or calculated measure of variable such as mean, standard deviation, variance, and etc. Probability is a very important concept in statistics. Please watch the archived video and read the references and let me know if you have any questions. I did not include anything about probability in this overview, so I don't overwhelm you with too many videos. Probability distribution is a table or an equation that links each outcome of the statistical experiment with its probability of occurrence. Let's look at an example. Suppose you flip a coin 2 times. This simple statistical experiment can have 4 possible outcomes: head-head, head-tail, tail-head, and tail-tail. Let variable x represent the number of hits that result from this experiment. And the variable x can take on values 0, 1, or 2. So the probability distribution of the random variable x would be as shown in this below table. If the number of hits are 0 in the experiment, the associated probability would be 0.25, which is the outcome would be tail-tail if there are no heads, divided by the 4 possible outcomes for this experiment. If the number of heads is 1, then the probability would be 0.5, because we could have the outcome as head-tail or tail-head from these 4 possible outcomes for this experiment. And if the number of heads are 2, then again the probability would be 0.25, and it would be head-head divided by the total number of possible outcomes for these experiments. Cumulative probability refers to the probability that the value of a random variable falls within a specified range. For the flip the coin twice experiment that we were looking at earlier, the cumulative probability distribution of the random variable x would be as presented in this table. If we are looking at the probability of x less than or equal to 0, which is probability of x equal to 0 because the possible outcomes for x are 0, 1, or 2, then it would be 0.25. If we look at the probability, the cumulative probability of x less than or equal to 1 would be the sum of probability of x equal to 0 plus probability of x equal to 1, which would be 0.25 plus 0.5, which equals to 0.75. And the cumulative for probability of x less than or equal to 2 would be the sum of the probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, which is equal to 1. Probability distribution determines how likely it is that any specific measurement is in the population. Depending on the data that we have, we may have different distributions or shapes of data. In this course, you'll be introduced to 4 types of distributions: the binomial distribution, the Poisson distribution, the normal distribution, and the standard normal distribution. The binomial experiment is a statistical experiment that has the following properties. The experiment consists of n trials that are repeated, and each trial can result in just 2 possible outcomes. It could be success or failure. The probability of success is denoted by P, and it's the same on every trial. And these trials are independent. That means the outcome of one trial does not affect the outcome of the other trials. For example, the flipping a coin twice and counting the number of times the coin lands on heads is a binomial experiment, because first, it's a repeated trial as we flip the coin twice, and second, it has only 2 possible outcomes, heads or tails, and third, the probability of success is 0.5 on every trial, and fourth, the trials are independent. That is, getting heads on one trial does not affect whether we get heads or tails on other trials. A binomial distribution or binomial probability distribution is a distribution that results from a binomial experiment. Suppose a binomial experiment consists of capital N number of trials, and the results are lowercase n successes. If the probability of success on the individual trial is P, then the binomial probability is calculating using the formula presented in this slide. A Poisson experiment is a statistical experiment that has the following properties. First, the experiment results in outcomes that are classified as successes or failures. Second, the average number of successes, which are often presented as lambda or mu, that occur in a specified interval is known. Third, the probability that a success would occur is proportional to the size of the interval. And fourth, the probability that a success will occur in an extremely small interval is virtually zero. Please note that the specified interval could take many forms. For instance, it could be a period of time, a length, an area, a volume, etc. The Poisson probability distribution is a distribution that results from a Poisson experiment. The formula for Poisson probability distribution is as indicated in these slides. And the parameters for Poisson distribution are K and lambda, and K refers to the successes that occur in the Poisson experiment, and lambda is the mean of the successes. In this formula, E is the base of the natural logarithm system, which is equal to 2.71828. It's a constant. And lambda is the number of successes that occur in a specified interval, and K is the actual number of successes that occur in a specified interval. The normal probability distribution is the most important and most widely used distribution in statistics. The features of normal distributions are they're continuous, they are symmetric around the mean, the median, and the mode of normal distribution are equal, and the area under the curve is equal to 1. And normal distributions are denser in the center and less dense in the tails. Normal distributions are defined by two parameters, the mean and the standard deviation. The graph of a normal distribution depends on two factors, the mean and the standard deviation. The mean of the distribution determines the location of the center of the graph, and the standard deviation determines the height and the width of the graph. When the standard deviation is large, the curve is short and wide. When the standard deviation is small, the curve is tall and narrow. All normal distributions look like a symmetric bell-shaped curve. That's why a lot of times it's also named as bell-shaped distribution. And there are times it's also referred as Gaussian distribution. The formula for normal probability distribution is also presented in this slide. The other basic feature of the normal distribution is that 60% of the area of the normal distribution is within one standard deviation of the mean, and approximately 95% of the area of the normal distribution is within 2 standard deviations of the mean. The standard normal distribution is a special case of the normal distribution. It's the distribution that occurs when the normal random variable has a mean of 0 and a standard deviation of 1. The central limit theorem is the most profound concept in statistics. The gist of it is that the sample mean would be approximately normally distributed for large sample sizes, regardless of the distribution from which we are sampling. The theorem states that, given a certain conditions, the arithmetic mean of a sufficiently large number of iterates of independent random variables, each with well-defined expected value and well-defined variance, will be approximately normally distributed, regardless of the underlying distribution. This theorem allows us to use normal and standard normal whenever we compare means for sufficiently large sample sizes. The other very important topic to be discussed this week is power, and in general, power analysis. This is directly related to your assignment that's due Sunday. Power analysis has 4 components: the statistical power, significance level, effect size, and sample size. Please watch the archived video that has the detailed information about power analysis and let me know if you have any questions. Here in this slide, I just want to present some very, very commonly used statistical formula. The mean, the variance, the standard deviation of the mean, which I'm going to talk about in the next 2 slides. And it's also called as standard error, the proportion, and the variance of proportion. It's important to know the difference between the standard deviation, which describes the spread of individual observations, from the standard error of the mean, which describes the spread of the mean of observations. When we compare individuals, we use standard deviation. When we compare means, we use standard error. The formula for standard error is as simple as the standard deviation divided by the square root of the number of observations. Standard error shows how good the data is. Let's look at these 2 experiments. The first experiment has only 2 observations, and the second experiment has 10 observations. Looking at the 2 experiments, the second experiment appears to have more observations and values that are closer to each other. However, if we calculate the mean and the standard deviation of the 2 datasets, as shown here, they're identical. Both of them have a mean of 12 and a standard deviation of 0.825967. Hence, the mean and the standard deviation couldn't tell how different the 2 datasets are. However, when we calculated the standard error, as shown in the figure, there is more variability of the mean for experiment 1 compared to experiment 2. For experiment 2, the mean may be as low as 11.739 and as high as 12.261. However, for experiment 1, it could be as low as 11.416 and as high as 12.584. This was the discussion for this week. Please let me know if you have any questions. You can post it on Ask the Prof, and I would be able to respond to your questions. Thank you and have a good week.